not working. It's not copied. What's happening? Let me see. Okay, you can run from there if you want. Thank you. Again, we have some technical glitch to overcome. All right. So in the morning, I gave you a lecture on overview on global energy scenario, Indian energy scenario in India, where it stands on bioethanol, and they're doing 1G okay, and the 2G is still a challenge. Okay. I'm going to go dive in this lecture on more into 1G and 2G technical stuff, how it is being produced, ethanol. Okay. Some perspective, historical perspective on energy use. In India, traditionally, we use this cow dung and dry cow dung, and even in rural villages, we go, you can see that people use that for energy source. And then in Africa, they use wood as a main energy source for cooking and heating purpose. We can do better. Okay, that's been traditionally followed, but it's very inefficient. We can do better. Okay, in the temperate countries and Western countries, wood is traditionally been a biofuel crop. In the temperate climate areas, it's cultivated approximately 20% of the land in Western Europe and North America. Not only used for food, but also for feeding the animals. So it's farming and for laborers and horse. 20% of the production of oat is heavily used in temperate countries. Okay. So let's talk about non-renewable energy. Just go back to very fundamental thing. We talked about non-renewable energy of petroleum, coal, natural gas, okay, and nuclear power plant. What's happening here?
Aliste అప్పుడు సార్
Can we go back to, okay. Full slide mode. Yeah, can you reduce the size? Yeah, move it down. Yeah, thank you. Yeah. So if you look at the traditional form of these energy source, we had this natural gas and crude oil found because of dead marine animals, plants, and microorganisms. They're buried in the bottom of the ocean for millions of years, and then it's because of it's close to the earth crust, heating mantle, and high pressure. All these organic matter converted into crude oil. That's what happened millions and millions of years ago. That's how we got the petroleum in the first place. Come on. Can it move it? Yeah. Next slide. All right. Here I got it. Yeah. Go back. So these sediments get buried deeper and deeper, and with the temperature and high pressure, the microorganisms, the sediments turn into gas and oil. You can see that organic rich sediments, and you have the dead organisms develop into crude oil, and then over a long period of time, oil and gas move upwards through tiny pores in the rock, and oil and gas trapped under impermeable layers of rock, and can be taken out using drilling, oil drilling and powerful drills. So that's how an oil and natural gas formed over millions and millions of years ago. It's basically biomass. The dead plants, dead marine organisms, microorganisms is what we are using as petroleum. Okay. So when we extract oil and gas, what you do, we can burn and heat water and steam it and propel and get electricity. And we can also use crude oil to turn into jet fuel, petrol and diesel to run our cars. When oil and gas get burned, they release carbon dioxide, and that's a global greenhouse gas problem. That's one of those environmental effect of burning fossil fuel. So the foundation of modern society, the lifeblood of modern society, the price we pay for is this environmental disaster we are experiencing. The last century is an oil economy century. Okay, so petroleum is a non-renewable source. As I said in the morning, it took millions and millions of years to form, and our use has been unsustainable. All right. So we are finding modern technology to drill oil. The primary extraction is when you drill hole. This oil in high pressure, they just gush out. You don't need to do anything. The oil comes out and is like a geyser. And then the secondary extraction, we use the steam at high pressure, and we call that fracturing or fracking. We get more oil. And then we have tertiary treatment. We do the Maillard process, microbially enhanced oil recovery. All the well that dried up, we put microorganism into that with the carbon source. The bacteria grow and release their product like enzyme and gas. It will release the oil that trapped in the crevices and of the rock. And then after years, then you can take the oil out. So we are finding technology of extracting this oil that took millions and millions of years to form. So we are getting it out, and it is not sustainable. It's going to run out at some point. Okay. So that's why green technology is finding ways to find method that we can use it sustainably and in a non-toxic form. The most urgent issue of green technology is develop alternative fuel that is usable with the infrastructure we have, which is our liquid mode of transportation. We need liquid fuel, right? So replace the gasoline car with ethanol blended or ethanol car. Okay. So how do we sustain this green technology? These 5 points. The green technology is sustainability, cradle to cradle design. It's also source reduction, innovation, and viability. Okay, let's look at sustainability. So when you produce oil, when you produce the green technology, it is sustainable because it's closed loop. So you get the plant, and plant use carbon dioxide, and the carbon cycle is closed, and you can sustain. As long as sun is there, we can produce this sustainable way of green energy. Okay, cradle to cradle design is you are creating products that can be fully retained and reused. You don't see any waste here. Okay, source reduction, you are reducing the waste and pollution by designing the pattern of production and consumption, which is everything we produce is completely cycled back, nothing is going to waste. Okay, and then innovation is developing alternative technologies, which there is a challenge and we still have to meet, and we are finding alternate technology. And viability is to create center of economic activity and technologies which will give jobs and improve the economy of people in the rural communities. Okay, so you don't have these migration issues, so people can stay where they are and try to find the way to improve their life. So, and just to re-emphasize, the countries that need more energy in the future and is China number 1, all right, followed by US, and the third is Western European countries, all the Western, and the fourth is India, right? That many million ton of energy in the next 2 decades in 2035. That is energy demand forecast. So India is right there. So we are number 4 in the world in terms of energy demand. Okay. So as I again mentioned in the morning, so if you look at the various energy source, petroleum, natural gas, coal are the dominant one. Then we have other thing in certain percentage we use. In 2040, you can see the percent use of coal, natural gas, oil going to go down. Not very high, but it's going to go down. And then you see the renewable going to go up because of technology and people realizing the emission of CO2 reduction and environmental issues, all that. We are projecting less use of conventional energy source and more use of green technology for our energy demand. Okay? So the problem of energy for people that where they need is an imbalance. Okay? We are the number one populous country in the world, but our conventional energy is not there. We import from other countries. Okay? There is a supply and demand problem. So demand is high, but our supply is low. That's why we have to import crude oil. Same thing for China. U.S. is in a better position because U.S. produce more oil currently, and they are going to have the similar problem in the future. They are going to run out of oil soon. Okay? So the cause of demand is what it's creating is an example here is look at the transportation, how it changed 50, 60 years ago from horse-drawn and cattle-drawn buggies to modern car use and electricity use. So increase in urbanization, change in lifestyle, usage of fuel-driven transportation. So it improved the lives of many people. It also become unsustainable and also create environmental issues. So solution for energy crisis is biofuel. Biofuel can be used to produce liquid fuel and gaseous fuel. Liquid biofuel is bioethanol, biobutanol. Gaseous ethanol is, biodiesel also liquid. Gaseous ethanol is biomethane, biohydrogen, and syngas, and biohydrogen, which is methane and hydrogen in the anaerobic digestion process. And today I'm going to talk about the bioethanol production, 1G and 2G technologies. So the motivation of bioethanol, I don't have to re-emphasize again, threefold. The 1G is basically the use up of damaged crop, that is, rice that cannot be used for consumption, for energy production, and then it's less air pollutants from vehicles. When you put blended ethanol, you use less gas, so less emission, and then less open biomass burning, because you're using some of the biomass for ethanol production. So 10% ethanol blending India achieved, and 15% is already there. 25% is their goal of blending ethanol. Okay? Another motivation is the environmental problem. So we have this the smog issues in Delhi and in Beijing in China. So as a result, this air pollution during the harvest season, farmers burn their crop after they harvest. That causes a big problem of public health problems, and it happens every year, and we're not having any solution so far. So when you use biofuel, it controls air quality because ethanol has 35% oxygen. It burns better compared to conventional 100% gas in your car. So adding oxygen to fuel results in complete fuel combustion. And gasoline containing, again, 10% ethanol blend can reduce your smog and reduce your carbon monoxide emission, particulate matter, and volatile organic compound. So those are added advantage of adding ethanol blend or using ethanol as your fuel source. Okay? So what is ethanol? So ethanol is a C2H5OH chemical. It has this oxygen in its structure, which makes ethanol a better fuel, make a complete combustion of your gasoline engine. So how is fermentation reaction works? It's fermentation is an anaerobic reaction. Glucose, most of the time it is yeast is our biocatalyst. Sometimes we can use recombinant bacteria like E. coli, which I'll show you in my research. Glucose is fermented to make ethanol and carbon dioxide. You can make from one glucose molecule. You can, by fermentation, you can make two ethanol molecules, two molecules of carbon dioxide. So if you look at it, glucose is basically goes through a process called glycolysis. In glycolysis, glucose is a 6-carbon compound broken down to a 3-carbon compound called pyruvate. Okay? From one glucose molecule, you can make 2 pyruvate, and then pyruvate undergoes fermentation reaction with the right biocatalyst under anaerobic condition. So the pyruvate is converted to 2 ethanol and 2 carbon dioxide. So that is biochemically what is happening in ethanol production. Okay? So let's look at a little more. So you have glucose. So glucose goes through glycolysis. During this process, you make the organism makes 2 ATP because organism need energy, right? So by breaking down, it gets net gain of 2 ATP. So it goes for organisms to use as energy. And at the end of the glycolysis, you make 2 pyruvate molecules. And then when you go through fermentation reaction, it goes through this NAD regeneration, nicotine adenine dinucleotide, which is our electron transport carrier. Electron here is the hydrogen that is coming from glucose when you break it down, right? So when this electron carrier carries NAD, it becomes NADH with the hydrogen in it. Okay, so during this fermentation process, NAD is regenerated and recycled back. It goes to glycolysis and comes. So everything is recycled. It's a more efficient way of converting the process. Everything is used here. So the pyruvate is converted to 2-acetaldehyde, which is further converted to ethanol, going through several biochemical reactions. And during this process, NAD is recycled. The end product of this process is from one glucose you make 2 ethanol. Okay? So let's look at grain ethanol, which is our 1G, first generation ethanol, a product of energy. So ethanol generally means, in this case, grain alcohol, which could be from your corn or sugar cane, use of the whole grain. We can also use potatoes, and so you can see in the U.S. mainly they use corn. In Brazil they mainly use sugar cane to make ethanol in 1G plant. So it's very, if you look at the energy efficiency, even though to grow crop for energy purpose, you are going to use conventional gasoline, right, to plow the land, to put the stuff in the ground, to make the plant grow and to harvest back. But if you calculate, there is a positive net energy gain from 1G generation of ethanol. Energy output to input ratio is 1.6. For every 1 energy you put in, you get 1.6 energy back. So it's a net energy gain, even though it's not very efficient way of using 1G ethanol, because you're using conventional gas to make this plant, right? But even then, it is still an energy efficient way to get ethanol. Okay? But there is another debate, which is food and fuel debate. So do you want to grow crop for, make energy, or you want to, grow crop for food because of increasing population? So to avoid that, we need to go to 2G ethanol production. So let's compare within gasoline versus ethanol some of the properties. Okay, so look at gasoline, and in Brazil they use E85, which is 85% ethanol blend. Octane number in gasoline is range from 86 to 94. In E85 ethanol, the octane number is 100. Main fuel source for gasoline is crude oil. In E85 is corn grain and agriculture waste in 2G ethanol production. Energy content in gasoline, you have 109,000 to 125,000 BTU. Whereas in E85 it's less, 85,000 BTU. Energy ratio compared to gasoline and ethanol blended, 85% ethanol blended fuel, it is 85% to gasoline. Okay, it's less. Okay? The physical state, both are liquid fuel, so you can use the current infrastructure to use ethanol to run your car, do your other activity, whatever gasoline does. You can use the E85 ethanol in your process. You don't have to reinvent new engine or new things. Okay. So conversion of starch. So we started from glucose, right? So where glucose come from in 1G? Glucose come from the grain. The grain is made up of basically the polymer, which is starch. Starch is 100% glucose, and it is put together by alpha-1,4 linkage from one glucose to another molecule. You break that alpha-1,4, you break the starch, and you release 100% glucose. So that's the first step. So when you get the grains, what they do, they have to release glucose from the carbohydrate, in this case starch. So they have to add this hydrolysis step by adding enzyme like amylase. Amylase will break down the starch and release glucose. Okay? Then the steps are the same thing we just talked about in previous slide. You go through glycolysis and goes through fermentation reaction and produce ethanol. So you have to add, when you add grain, you got to add a hydrolysis step. In this case, use enzymatic hydrolysis, or you can also, if you don't want to use enzyme, you can use steam. You can heat. When you heat the grain, you release glucose too. Okay? So that's biochemically, that's what's happening in 1G. When the grains are going through hydrolysis, you use alpha-beta amylase, and also you get your glucose, and then you go through the same step we talked about, glycolysis and fermentation, you make ethanol. So we have one more step of hydrolysis when you start from grain, okay, to get the glucose out of starch. So let's look at a little more detail of biochemistry, what is happening. In the yeast is the most favored biocatalysis used. Yeast, in this case we talk about yeast. We have the process of glycolysis, fermentation. For 5 carbon sugar like pentoses, you have pentose phosphate pathways. Okay, so without going too much into detail, you can look at the pentose 5-phosphate here, right there, and you can see glycolysis, and you can end up in pyruvate, goes through fermentation, you make your ethanol, right? So here is your biochemical pathways. These are the 4 different pathways that yeast use to produce your ethanol. Okay, simple pathways, already well established. We know every step, what enzymes are used, how much energy is needed for each step, and how yeast can be manipulated to make highest ethanol yield possible. So we worked out this to the perfection. So we can make theoretical yield of ethanol. So that's why 1G ethanol is a mature technology. You cannot make any more efficient way of producing ethanol. We did that. Right? We make that. 1G is very successful. Okay? The only problem in 1G is the feedstock. The feedstock is food source. Okay, that's a major problem. Okay? So we achieved, studying basic biochemistry and microbiology, we achieved the successful production of ethanol. That's a basic biochemistry over there. Okay? To put it in the schematic, here we have your corn or wheat or any grain that you want to make your ethanol. It goes through a milling process. After milling, you get the meal and you go through the hydrolysis step. You add your amylase enzyme that makes your glucose, and you make this mash come out of with glucose 100%. Go through fermentation. Yeast is your biocatalyst organisms, and that fermented mass is producing ethanol. You produce a lot of product here. Okay, then ethanol is what is distillate. You get your ethanol for your fuel source, and you have this dry distillate grind soluble, we call that DDGS, which is high and rich in protein, which is an animal feed source and in high demand in the US. It goes right to cattle farm, so nothing is wasted there. Okay? So processing step for converting corn grain to ethanol is, those are the steps: milling, hydrolysis, fermentation, product separation. Okay? So let's go a little more detail. So that's a step right there for your making ethanol from grain. Okay? Milling, you grind it up. Liquefaction, you mix with water and heat it. Saccharification, you add enzyme, convert starch to glucose. Fermentation, you add yeast to kick off the fermentation reaction. It takes the glucose, convert them to ethanol and carbon dioxide. Then you go through the distillation step to separate your ethanol from the solids, and you go through dehydration to remove the last bit of water from ethanol, and you go through denaturation step, so you make it unfit for human consumption, so you only can use it for your gasoline engine. And then the co-product, the distilled grain, goes to livestock feed because it's rich in protein. So, and the CO2 that produced, it can be compressed, and you can use the CO2 for various use for CO2. So here is the whole process is mature technology. We know every problem solving, everything, and then the yeast is available from yeast manufacturers. So everything in good order to make ethanol from ONG ethanol technology. Okay, very mature technology, commercially successful in US, in India, and Brazil. Okay, it's a commercial plant in 1G ethanol production in the US. We have more than 200 plants, make 17 billion gallons of ethanol every year. And most of them are in corn belt states, in the Midwestern state. That's where the corn is produced in abundance. That's where all these ethanol production factories are located, fermentation plants are located. So we have more than 200 of them in the US. Okay. So US is number one producer of ethanol, followed by Brazil. Then let's look at 2G, what's happening in 2G, which is the second generation ethanol production. In this case, cellulosic ethanol is made from cellulose, which is one of the polymers of plant. Cellulose naturally provides structure to the plant. It's part of the three polymers that make the plant rigid and gives the plant structure: lignin, cellulose, hemicellulose. So the sources of feedstock are waste come out of the agriculture operation, like corn stover, sugarcane bagasse, sawdust from wood mill, and paper pulp mill waste, and switchgrass, which is energy crop. You can grow this grass, which is high in cellulose, high in hemicellulose. And these grasses can grow everywhere, marginal land where you don't have agriculture operation. Okay? So you don't compete for food production. So those are the advantage of 2G ethanol production. All right, concept here is you collect the residue. That's the problem. I talked this morning about transportation, how you take the residue to the process center, right? Because of its bulkiness, because of light density, all that issues. That need to be worked out still. And then you remove the lignin by various pre-treatment process. When you remove the lignin, you get the cellulose, hemicellulose come out. Cellulose is made up of 100% glucose. And this time, the glucose are put together in a bond called beta-1,4 linkage. The beta-1,4 is hard to break than alpha-1,4 in starch. Okay? So that's why you need enzyme cocktail, various enzymes. So to break alpha-1,4, you need only one enzyme, amylase. For beta-1,4 breakdown, you need multiple enzymes to break it down, a little more harder. That makes sense, right? Plant have this for purpose because it protects the plant. You don't want cellulose to degrade faster, right? Plant needs that as give a structure to the plant. So that's why nature made it cellulose very hard to break it down. Okay? To break it down, we add cocktail of cellulase enzyme, which release the glucose, 100% glucose. Then, when you get the glucose, then the steps are exactly same as 1G, no change at all. All you're doing is getting the glucose out of the residue from agriculture crop, and then everything else is already there from 1G technology. So let's compare the feedstock. Okay, the feedstock all around the world, from forestry, from wood, commercial forestry, from wood production to rapeseed oil, from maize, sugar beet, energy crops like miscanthus and switchgrass, corn, wheat, jatropha. So we have all this. What the energy industry people do, they compare it to solar panel in Kalahari Desert, where you have the lot of solar availability. They compare the energy from each plant, and you can see the tropical plants, the sugar cane, they are really good compared to corn and other residue. Okay, because of the way this residue, I told you this morning, the variation in cellulose, hemicellulose, lignin, and then the energy come from is different from feedstock to feedstock. Okay? So let's look at how plants are put together. The three major components are lignin, cellulose, and hemicellulose. And if you look at the plant, any plant, and we have the lignins are put together by polyphenolic compound that combines the cellulose, hemicellulose, and protect them. And when you look at cellulose, it comes in microfibrils, and that also has crystalline cellulose, which is all right here. It's like a crystalline cellulose. And cellulose, as I said, is 100% glucose. Cellulose, when you have cellulose, it broke down to cellobiose and then to glucose. Okay? And then hemicellulose is made up of pentoses and hexoses, which is 5-carbon, 6-carbon sugar. So here is the more details of what lignin is made up of. Lignin is made up of these three common phenolic compounds: coumaryl alcohol, corypherol alcohol, synapyl alcohol. And these phenolic compounds are put together to make your lignin structure. Okay? And then when you look at cellulose, it's 100% glucose. Then when you look at hemicellulose, you have the 5-carbon, 6-carbon sugar. Okay? So these two can be used for your fermentation to make ethanol. Phenol cannot be fermented, but phenol, this lignin compound, can be used as for burning furnaces and stuff. Okay, but these are the material that you need to get it out and get the sugar out and route it through your fermentation technology to make your ethanol. So a little more details on how they are put together in nature. So this is how it looks like. You have your other compound. The three major ones are cellulose, lignin, and hemicellulose. And this is how lignin look like. All those phenolic compounds put together to make the rigid structure. And then if you look at cellulose, it's 100% glucose. Then you look at hemicellulose, you have these pentoses and hexoses made up of, we commonly call xylosic sugar, but it has glucose, mannose, galactose, all of them are there. They have a 5-carbon, 6-carbon sugar to make your hemicellulose. Okay? So let's look at the composition of these three major polymers. It varies from feedstock to feedstock, but the range is the range right there. So if you look at all the feedstock, the lignin is 15 to 25%, the phenolic compound. Okay, the xylosic sugar in the hemicellulose is 23 to 32%, and cellulose is anywhere from 38 to 50%. Some feedstock has 50% cellulose, highest. Okay, so these are the major range of this natural polymer that make plant. That's why you have feedstock variation of how much cellulose is in corn, how much cellulose is in miscanthus or switchgrass. It's all different composition. Okay. So to make ethanol from 2G makes sense because it completes the carbon cycle, it completes the energy, it completes the loop of carbon cycle, so you're not producing CO2 into the atmosphere. Okay? So let's look at how that happens. So we have solar energy. Solar energy is used by the plant, convert sun energy with water, and through photosynthesis using the carbon dioxide from the atmosphere, it fixes the carbon dioxide and make more biomass, and we make this cellulosic ethanol, and we use the cellulosic ethanol to burn it in the car, to run our car. The car emits the carbon dioxide. Carbon dioxide goes back by the plant, and the cycle is complete. Nothing is going into the atmosphere, so it's not producing greenhouse gas. So that's why this is environmentally friendly when they say it. Why? Because carbon cycle is complete in this loop. Okay. There's another attraction of using green energy. Okay. So let's look at this cellulosic ethanol. How we are going to do pre-treatment process. The pre-treatment process is the rate limiting step and hydrolysis and pre-treatment process. And you take this cellulosic ethanol. We use a lot of pre-treatment method out there, acid, alkali, ionic liquids, and ammonia fiber expansion. And so once you get that, lignin is removed, you got the cellulose and hemicellulose. And cellulose and hemicellulose, you treat them with a cocktail of enzyme, you get your sugar out, you get your lignin. Lignin can be burned in power generation and produce electricity. And you get the sugar, go through the fermentation process and distillation, and get your cellulosic ethanol. Is this environmentally sound? If the concept is complete, if it is economically viable, yes it is. Okay. We have a long way to go because of the cost and some technical difficulties in the first two steps. The first two steps are these pre-treatment and enzymatic hydrolysis. The rate limiting is enzymatic hydrolysis. The enzyme is high, cost is high. And then we have in the morning we discuss about digestate problem pre-treatment. Depending on what pre-treatment you use, you have the digestate that gives problem in the downstream processing. So let's the concept of biorefinery. You have all this plant biomass, and we can use this as biorefinery concept. So you have your feedstock, various feedstock from municipal solid waste to agricultural residue, forest residue, energy crops. And we have this technology. We have biochemical route, we have thermochemical route, and we have the various market for the product, right? So if you look at the feedstock, we can go either this biochemical route and produce your ethanol, organic acids, hydrogen, all kinds of product you need if you route it through fuel. Or you can take the sugar and make fine chemicals. Okay, that is more economically attractive. Okay, and then or you can take thermochemical route, you combustion process, gasification, pyrolysis, chemical catalysis, and then separation technology. You can make electricity, heat, steam, plastic, and chemicals. You can make a lot of things. You can make syngas and convert a lot of different product in thermochemical route. Okay, so we have these three different ways to make what you want out of this biomass. Okay. So if you look at the municipal waste in the U.S., the composition is mostly lignin. I mean, it's a biomass is basically cellulose, hemicellulose. So that could be used for energy generation. So if you look at it, it's 37 to 38% paper and paper product, which is basically cellulose, hemicellulose, lignin. And then we have yard waste, which is basically after they cut the grass, and that goes into the waste. And then food and wood waste. So if you take all that, it's 70% of what you throw. Okay, then you have other separation. You have glass and metals and plastics and textiles and rubbers, all that. Potentially, you can make energy from that, cellulosic material. Okay, so that could be a feedstock for energy generation. So let's look at overall how much this energy generating biomass is available. If you add all that in the pie, you can produce 623 million dry ton of feedstock available every year, right? That is equivalent to 16 quadrillion BTU. That can meet 1/3 of energy need of US. If you do that, feedstock is available every year. It is renewable and sustainable. Okay, so all the sources are given here. You have agriculture, crop residue, forest residue from your wood product. You have your solid sludge from sewage, municipal solid waste, and then your potential energy crop like switchgrass, miscanthus that you can use in marginal land, not arable land, agriculture, and not competing with agriculture. If you take all that, we can meet 1/3 of energy use of US. Okay. So let's look at in little more perspective in terms of how much ethanol you can make. So annual projection for cellulosic ethanol in the US is make 50 billion gallons of waste to make ethanol, 50 billion gallons from the waste, and then you can make 80 billion gallons of ethanol every year from to estimate for 1/3 and transportation need, and you can make 114 million acre that is not used for agriculture to make energy crop, switch crop and miscanthus, and that will produce 165 billion gallon of ethanol, which is equal to 108 billion gallon of gasoline. Okay, so you can see the math, and it is workable, it is doable to make ethanol from 2G and make it sustainable and in a green energy way. Okay, green technology. So let's look at the motivation. The process used to grow and collect biomass, including any associated land use. You're going to still produce and some pollution to make your crop, but the schematic is simple. You use your feedstock supply, make your supply chain really, really good. So you got your farmers doing that, transportation taken care of, it goes to the processing plant. And then you have biofuel production and biofuel distribution, biofuel end use, and that's a motivation in the process of making it smooth, make it the supply chain all worked out. Okay. So you had to treat energy from biomass as biorefinery concept, how the oil industry works. Okay. So I told you millions and millions of years ago, it's all biological material that turn into oil, right? Crude oil. So we take the crude oil and we make a lot of product from the crude oil. So these are the various products listed here from the crude oil. So now you get your crop, whether it's corn, sugarcane, ag waste, and convert them to C5 and C6 sugar and treat C5, C6 sugar as a crude oil. And you can make from C5, C6 sugar to make the same product that you're making from oil. Okay? So you are just replacing the crude oil with the biomass product of 5-carbon, 6-carbon sugar. So we call that the biorefinery concept. Any product you make from crude oil, you can make from biomass material. Okay? Some of the advantage of bioethanol is it's environmentally friendly. We talked about it. Agriculture benefits from it. Farmers have the better product to make, and also food security from 2G generation. So in the terms of environment, it has a better biodegradability, carbon dioxide neutral. It's higher, better fire safety, less greenhouse gas emission, clean burning, low toxicity. In the food security point, a reduced dependence on oil, agriculture diversification, so farmers can have better diversification of crops. And what you get out of that, you can, from lignocellulosic ethanol, you can make energy, you can make fuel, a lot of different, like a diesel, gasoline, hydrogen, jet fuel. You can make a lot of chemicals, as I said, in biorefinery concept. You can make any kind of chemical you want in the sugar platform. You get the sugar and make the organism, choose the right organism to make any kind of product you want, whether you want short chain fatty acid, long chain fatty acids, acetone or solvent. microorganism can make it. So that's your biorefinery concept of using biomass into various products that you want to make. Let's do what is the 1G, 2G, 3G, 4G, what are they talking about? I will just discuss 1 and 2Gs. 1Gs is the first generation ethanol coming from the mainly the corn and sugar and all those food crops. 2G is the basically lignocellulosic ethanol production. 3G is algal biofuels. 4G is biohydrogen and fine chemicals. Okay, so that's the classification of what is 1G, 2G, 3 and 4G generation biofuels. Okay. So again, going back to second generation biofuel, so lignocellulosic is a better and alternative way to make ethanol. It can be grown on barren, uncultivable land for food production. Need less amount of water to grow because these are wild grass. Does not interfere with your food chain. Is available in ample amount because you don't have to use fertilizer, you don't have to use any pesticide. These are wild grass. And a mixture of lignocellulose biomass circumvent problem found in the biomass availability issues. It has high yield per hectare because these are wild grasses. So they can grow up to 20, 30 feet grass, switchgrass and miscanthus. Okay. All right, the problem again is to get your polymer out where you have the lignin, you get the hemicellulose cellulose out of this plant holding it together. Again, going back, what is those three major polymer, the lignin, cellulose, hemicellulose. Structurally, this is what they look like. We want to get them separated. And if you compare, switching back to why ethanol is more sustainable and it's also attractive, is the crude oil price fluctuation. Crude oil price changes depending on geopolitical event. And in the 2000, when the second Bush was in office, the crude oil price went up to $140 per barrel, right? And that was a big shift in U.S. government policy to try to make energy independence, reduce import from Middle East. And so Bush created a policy to switch everything to ethanol production, especially to 2G ethanol production. Let's talk about some misconception out there. So let's just quickly put out what are those misconceptions. Where is that? So the basic energy fact, we do not need energy. What we need is service that energy provides, right? What are those services? Heat, light, and mobility, all right? We need those three services. That's where the energy we are trying to get. Energy has fundamentally different qualities. The carriers are not interchangeable. All BTUs are not created equal. Depending on the source, it's different. Industrial society literally stops without liquid fuel. We need liquid fuel. Okay, liquid fuels, not energy are required. Mostly liquid fuel is what currently we are looking at. Okay, the electric vehicle may change, but currently the world needs liquid fuel. Okay. So just to show you the problem of our society stops without liquid fuel, we will have to go back to our horse-drawn buggies for our transportation. All right, let's look at some of the other issues about energy. So other social issues revolve around conventional energy. Okay, all energy carriers do not have equal strategic importance either. Coal, US and Canada have a large, China have a large amount of coal reserve, okay, coal reserve, and natural gas import significantly from mostly Canada and Mexico, the US, but now we are exporting, we are producing more in the US, we are producing more petroleum. And petroleum dependence undermines climate security, economic security, international security, and world stability. So when we are fighting for oil, in Gulf War and all that, it's going to have insecurity in the world. Okay, so another motivation to switch to green energy. Okay? So one more reason, biofuel including cellulosic are one of a small handful of petroleum alternatives that can provide national security advantage, so you don't have to depend on imports. It also has a large greenhouse gas reduction, economic advantage, and also from agriculture and forest residue, we can make ethanol, and also from energy crops. So these are some of the other reasons why biofuel is important. Let's go back to some of those topics we discussed. That's your first generation corn plant. So you have your corn kernel, hydrolysis, sugar, fermentation, distillation, drying, ethanol, co-product for animal feed. Okay, let's sum up the different schematic. This is from sugar cane. So you get your sugar out of sugar cane, and that goes through fermentation, distillation, drying, and you get ethanol. Okay, let's look at the second G. So you get cellulosic ethanol. You need the pretreatment, enzymatic saccharification. You get your sugar and goes through the same process. Okay, and then you have the thermochemical route. So you can have your corn stover, all the agriculture residue, forest residue, wood chips. You can get that thermochemical route. You can have a heat and power, fuel and fine chemicals you can make. So the biomass from 1G, 2G can do all this. Okay. So if you look at petroleum fuels and biofuels, some other problem about petroleum fuels, the commodity products, fuel, bulk, chemicals, semiconductor chip, potato, these two things are the final product. The two things involved in this, a cost of raw material and processing. Those are the two major costs when you make a product. How you get your raw material and how you refine your process economically, efficiently to reduce your cost. Okay? And the same model can be applied to your ethanol production. I'm going to go back to your petroleum and come back to ethanol, how this price varies from raw material to processing cost. Okay? So for gasoline, diesel, etc., the cost to make them depend on petroleum cost. How much your crude oil costs, that dictates your gas in your pump. When you pump your car, how much you're putting. And it all depends on your crude oil price goes up, your petrol price goes up, right? So it was just the reverse the other time. Crude oil was plentiful when it was first extracted out, and the processing cost was high, right? So I'll show you how completely it interchanged. So when you're making your ethanol comparison to petroleum product, you have this large margin to play with of the petroleum price, $10, $15 at the beginning to $120 of a barrel of crude oil, right? So if you make your processing cost of ethanol to fit this, you can work your ethanol better than petroleum price. Okay, I'll show you. The process is your research. The research to eliminate the processing cost, reduce the processing cost by doing efficient processing. So let's look at how it happened. When oil was first discovered, oil come out of the ground. You make a hole, it gushed out. The feedstock was cheap. $5 a barrel, $10 a barrel. The processing cost was expensive at the beginning. Okay, and the research and refine the processing over a long period of time, chemical engineers, processing costs came down. It flipped. You can see that, the second bar. Today's, your processing cost is, the blue bar is less. Oil, crude oil price is high. All right? In the future, the crude oil price is going to go up because your supply is getting less and less. Your feedstock is going to be really high. Your processing cost is thinner and thinner, smaller and smaller because of research, and you make this biorefinery really better and economically viable. Okay? The same design can be applied to ethanol production. So this is the same thing as what I'm talking about. Historically, petroleum was cheap, processing was expensive. Over research, we kind of flipped the chart. We kind of, processing cost is smaller, petroleum cost, production of petroleum is increased. Okay? We can apply the same thing to the gasoline, ethanol production. So this is what the Brazilians did. Brazilians completely switched from petroleum to ethanol. Okay, they don't import any gasoline. Everything is self-energy independent country. Okay, they use ethanol as their main energy source. Because of their processing, they perfected the technology. Okay. So look at how this is looking at biomass. The same picture. What happened at the beginning of oil industry can happen in ethanol production. Okay, so today we have more to process your biomass because our technology is not mature. That's why your R&D is important. You reduce the processing cost. In the future, your resource availability of biomass is going to be, your cost is going to be increasing. Okay, and you are going to reduce your processing cost because of research effort. Exactly what oil industry did for oil production and processing, this can happen for ethanol production. So research is important, cut the cost of processing to make various products. Other attraction is domestically produced fuel. You don't depend on import. Environmental improvement, rural jobs. It's going to create more rural jobs, make farmers, diversification of crops. So better economy in the rural economy is possible. So this is some of the 2G commercial plant in the U.S. Make so many million gallons of ethanol from straw to corn cob to switchgrass. You can see the list of companies, from Iogen to Alico to Abengoa Bioenergy to Poyet. So a lot of companies commercially successful in 2G ethanol production in the U.S. Okay. How do they do that? So I show you the map, the transportation issue. They have cooperatives for every 100 farms. In the U.S., farms are average 1,000 to 2,000 acre farms. So they have a cooperative. They have a collection center. They bring their residue and they densify the residue in the pellet size so they can carry them. Transportation cost is less. They go to the processing center, and then they have a pre-treatment and saccharification plant. And then once they get the sugar, it goes to their first generation plant. So they don't have to refigure and produce new factories. They kind of put these cooperatives in the farming communities in different places. You have a collection center, densification center, and you have pre-treatment facilities. And then once you get your sugar, it goes to your first generation plant. Okay? So that's what's happening in this schematic, how it was successful in the US. You have the biomass production, harvesting, storage. It's become a cooperative in a rural community. And then you have a pre-treatment plant and enzymatic. These two are in one plant. And you got your sugar, get from the cellulose, you got your sugar, and then it all goes back to the mature technology of 1G. Once you get the sugar, there's nothing else to do. It goes back to 1G technology. So these are the steps. They perfected it, putting in different places, so your transportation cost is less, densification of biomass, so you don't carry this bulk straw transportation issues, all that they perfected in the US, in the Midwest. Okay. So that's the schematically how it shows this is working in the US. Okay. So that's to show you more schematically how cellulosic biomass is done in the US. You got the pre-treatment, you got your solid liquid separation, enzymatic hydrolysis. They are also making enzyme right in the plant. I added that unit, so you don't have to buy commercial enzymes, so reduce the cost. And then you got the fermentation, and you make your ethanol, and you make your co-products. Okay. One of the preferred pre-treatment in the US is ammonia fiber expansion to remove the lignin. And how that works is, this is how it works. So you have your biomass, and the biomass is put in a reactor, and they are heated at high temperature, and then they add the ammonia gas, and it expands and releases the lignin. You get the cellulose, hemicellulose. Ammonia is recovered and recycled back, and the treated biomass go to the enzymatic step to get the sugar. So that's how AFX works for pretreatment. This is one of the matured pretreatment technology very commonly used in the US at a commercial level. Okay. The advantage of AFX is sugars are not degraded during pretreatment process, and there is no inhibitor, there is no digestate problem. So when you do pretreatment, you get chemical inhibitor like furfural, 5-hydroxymethyl furfural that inhibit your fermentation. You don't have that product when you do AFX. Okay. So compared to other pretreatment, there are so many pretreatment: dilute acid, alkali, ionic liquid. So AFX is very cheap economically. It costs $1.41 per gallon of ethanol using AFX compared to other. So this is the preferable one. The problem is it's patent technology, so you have to pay royalty to use this technology. So AFX is a reduced ammonia loading for recycling. Capital cost is less compared to other treatment technology. As this AFX still matures, they're predicting the cost of ethanol production going to go down to 62 cents per gallon of ethanol. This is what they're predicting. As the technology matures, I talked to you about the processing. This will happen in the future. Okay. So some of the socio-economic issue of when you make ethanol from biomass. So we have environmental improvement, rural economic development. We have less expensive food possible because you're not competing food versus fuel debate. Improved animal feed from the ethanol fermentation. You had this distiller, protein-rich distiller solubles. It's also less expensive, more abundant for human food. So let's look at how in India you can perfect this technology, the same concept. So you get these farmers producing biomass, you get your regional cooperative for collection center. So regional biomass processing center. And then you can have this feedstock come in, and then you get your densification process, and then you get your pre-treatment, but you need to come up with a pre-treatment. You cannot use FX because FX is patent. You have to pay for the royalty. Once you get that, this concept will work in India for 2G successful production of ethanol. Okay? So let's go back to some myth. There is in the internet, we have this lot of rumors about ethanol. Okay, usually. Because internet could be a curse. Could be people put all kinds of stuff in there. All right. So this is what's happening. Okay. People say ethanol has negative net energy. I want to clarify that. Gasoline net energy is worse than ethanol. All right. So and always this metric is irrelevant. People talk about bad thing about ethanol. Ethanol will drive up food prices. It happened once. We had food and fuel when corn was going to make ethanol in the U.S. The tortilla that Mexicans use, we call Mexican food, that price went up one time. It's a complicated question. There is no easy soundbite to answer to that. But cellulosic ethanol will make sense. You're not competing for food. Okay. Ethanol is bad for the environment. Compared to what? Right? People say ethanol is bad. Corn ethanol is superior to gasoline when you compare in several metrics. Cellulosic ethanol is even better. Okay? Ethanol will always cost more than gasoline. Ethanol you can make, the first sheet $1.20 per gallon. When they improve the processing, the costs go down. It's going to 60 cents a gallon in the future. Okay? So there are a lot of myths out there. People put these unwanted thing to make bad publicity in the internet. Okay. All right. The one problem in ethanol is you produce lignin. What are you going to do with lignin, right? So lignin in nature is needed for the plant. That's the purpose of lignin, to give rigid structure to the plant. So lignin has negative impacts on biofuel production because lignin impedes hydrolytic enzyme action. Lignin irreversibly bind to cellulase. Lignin degradation product inhibit fermentation because of phenol. Phenol is antimicrobial. Lignin is not fermentable. Okay, so these are some problem that people address. Okay, how you're going to separate the lignin when you do the pre-treatment, because lignin can cause some trouble in enzymatic saccharification step. So let's do step 2 involved that I went through this process, pre-treatment, get the cellulose, semicellulose, and get your sugar and do the ethanol recovery. Different techniques of pre-treatment out there. You could use any one that is workable for you. Acid, alkali, physical, high heating, high steam, a lot of things out there. The FX is costly mainly because it's patent. Ionic liquid is even more expensive because of the ionic liquid cost. Okay, the one that I prefer is biological. Use fungus. All right, fungus in nature can produce cellulase enzyme that will break down lignin. Yeah. I'm getting to that. That way called consolidated bioprocessing. We're getting to the technology of putting fungal gene into the bacteria. Okay? Yeah, okay. I got that. Yeah, it is hard to get your fungus grow, get your enzyme out. I'll show you the work that we did. So biological treatment, pre-treatment is what I prefer. You want to get these fungal microorganisms. They produce this peroxidase enzyme. You have manganese peroxidase, lignin peroxidase, and lacases. And these enzymes basically break down lignin. And you get your cellulose, semicellulose. In nature, that's what you do. When you throw your compost from your kitchen waste in the backyard, what happens? Fungus grow. Fungus break it down, the plant material. Okay, they produce these enzymes, lacases and peroxidases enzyme. So the idea is to when you are going to store your biomass, you spray the biomass with this fungus. and the fungus will break the lignin down, and you reduce your pretreatment cost. You use less acid, less alkali. That's the one way to do it. Another way to do it is DNA technology. You take a couple of these genes out of the fungus, put it in the bacteria, and the bacteria will make the same enzyme, break down lignin for you in one pot. Okay, so that's one way to do it. So enzymatic biomass pretreatment is what personally I prefer, because I'm a biologist, so I like to work with organisms. Okay, so there is a lot of advantage of using fungal enzyme instead of going through these AFAX and ionic liquid and acid alkali pretreatment. Another advantage is, if you look at all the pretreatment, if you look at the water use is high in the pretreatment process. You use a lot of water. When you use the organisms, fungus enzyme or fungus, the water use is really less compared to other pretreatment. Okay, so you can see all the different process, all the pretreatment process, lot of water use. Compared to biological pretreatment, the water use is less. Okay, so I prefer fungal enzymes as a pretreatment personally. So I'll spend some time with this. Okay, you can get enzyme also out of these bugs. These bugs like termites, gribbles, and other things. They eat wood, and they are processed inside by microbiome, different microorganisms living in the termite guts. Okay, they break it down, the lignin, release the sugar, make short chain fatty acid as energy source for the termite. So we can find unique organisms, high efficient organisms that can break the lignin down in nature. We can exploit them for our pretreatment purpose. Okay? So that's the goal, to try to get the pretreatment work biologically using enzyme system. So you use instead of using various pretreatment, you're going to use the enzymes or use the whole fungus. Okay, and then you go through, get your sugar out, go through ethanol production. So here's some example of when you use enzyme, when you use pretreatment, you can see same effect. Fungal enzyme work as good as conventional pretreatment method in removing lignin. Okay? So let me, the last few minutes, it still have time, right? Yeah? Yeah. I'm going to talk about my research of what I did, how I incorporated fungus into my pretreatment method. Quickly go through the process. So I don't want to go through the same process why I did the research, need for alternative fuels. Its advantage is the carbon neutral, it's a natural process of making biofuels. Currently account for 1% of world needs, so we need to make more biofuels, okay? But potentially you can, but technically so far we are not meeting the world what it needs in biofuel. So I got funding from U.S. government at Department of Energy because the mandate they have is to replace 30% of 2004 gasoline consumption by 2030 by ethanol. That means the U.S. has to make 60 billion gallon of ethanol every year. They right now make 17 billion from corn. They have to catch up with 2G. The 2G makes another right now they make another 3 billion gallons. So there is big, we only have shot 2030 is another 5 years, right? We have to make another 2/3 to catch up with the government goal. So make cellulosic ethanol as cheap or competitive as gasoline price, which is $2.33 per gallon of ethanol. That's the DOE goal to achieve that, Department of Energy. So I got funding, I got big amount, $7 million research project. My goal is, we got a lot of different aspects. I'm going to only concentrate biological aspect of the project. So Louisiana, where I come from, is a sugarcane state. They make number 2 sugar producer in the U.S. We have a lot of sugar cane, and we have a lot of marginal land. They produce energy cane. Energy cane has less sugar, more fiber. It has doesn't need fertilizer. It's like a grass. So we wanted to use this energy cane and show that it can be used as a biofuel product. So we used this particular energy cane, which is called the L02, because the advantage is low water, high fiber content, is a perennial crop. In the U.S., winter month, it gets cold. The sugar cane has to be harvested before cold. But this crop can grow without any problem. So we chose this particular energy cane for our research. So we did harvested this biomass, brought it to the lab, processed it, cut them into pieces for our fermenter. Try to get this pre-treatment work. We tried alkali, acid, and then our fungal pre-treatment. We tried to get cellulose, hemicellulose, lignin separated. First we tried all these three methods. Pre-treatment, we tried alkali, acid, and biological method without any, we just do the pre-treatment and do the fermentation without adding enzyme. Okay, just you got a little bit of sugar, come and see how much ethanol you are making. Try to compare these three methods. So the objective is to find the cost-effective means of producing ethanol from this energy cane. We want to compare alkali, acid, biological pre-treatment. Then we want to optimize pre-treatment condition, combine biological and chemical pre-treatment. So you want to share this? Anybody knows how to share this? The people cannot computer audio, or I see something. Can you share this one? There's somebody put the people cannot see my audio or video, it looks like. Is it okay? Huh? Okay, I think now it's gone. Maybe they can hear me. All right, let's continue if there's no problem with it. So I used in my lab weak sulfuric acid pretreatment, which is you soak in a different concentration of sulfuric acid for 24 hours, and triple rinse with DI water, and do fermentation without enzyme, okay, and see what happens. And then we did alkaline. We did increase the pH with sodium hydroxide, and did the same thing, alkaline pretreatment. Can you move that next? It's not moving. Okay, and then with the fungal pretreatment, what I'm using is whole fungus. All right, we're not producing enzyme, so we spray fungus and put them in a plastic bag, allow the fungus to grow on the sugar cane, and then we go into see how much lignin is removed. Okay, so we chose the best fungus, Phanerochaete chrysosporium, commonly known as white rot fungus. Then we have brown rot, Cereoporiopsis. Then put them in solid state fungal treatment in a bag and see what happens. Okay, and then we did the second step of enzymatic saccharification. We use the cellulase xylanase enzyme. Put the digestate in there and do the fermentation reaction. Then we did the recombinant DNA technology. We kind of modified the genes of the organisms. Used the E. coli because the yeast cannot use the C5 sugar, right? So we wanted to do all the sugars in one organism. So yeast only can use glucose. So we want to use C5. So we took some genes from C5 fermenting organism, put in E. coli. So one organism, but one biocatalyst organism can break down all the sugar and make ethanol. So we tinkered with the DNA without going into details, and we produced an organism, E. coli BR5, which can ferment C4 and C5 and C6 sugar. So here's a quick result. If you look at acid result without enzyme treatment, the different concentration acid 1% to 4%, you can produce ethanol, whatever the pre-treatment release some sugar, we can make ethanol. And this is alkaline pre-treatment, increasing the pH with sodium hydroxide with a little bit of hydrogen peroxide in it, and you can see that also produce ethanol. Okay. Then this is fungal pre-treatment, which is comparatively just putting fungus on it, it produces ethanol. Okay. And then what we did was we look at the sugar yield just without enzymatic saccharification. The fungus that we use, each fungus alone and combined fungus produce a little bit more sugar. All right. So we could potentially use this as a pre-treatment, biological pre-treatment, without going through a messy pre-treatment of acid, alkali and stuff. It's possible, just to show proof of concept. Okay. And then in order to reduce the acid concentration, we combine the biological pre-treatment with the weak acid. So here is sulfuric acid concentration of 0 to 2% with fungus during storage time. The idea here is you collecting the raw material, it's going to store in your storage facilities before it's being processed, right? It could be 1 week, 2 week storage. During this time, you spray the fungus. During storage, the fungus will gonna soften up the lignin. So your pre-treatment cost will be less because you're adding less acid in your pre-treatment. That is the idea behind it. Okay. So that's what we are showing. Fungal and sulfuric acid pre-treatment, you can see that ethanol produced. There is no difference statistically between a 1% to 2% ethanol. So we chose 1% sulfuric acid fungal pre-treatment instead of 2% sulfuric acid. And then we use this E. coli, that is recombinant E. coli. We put this C5C6 fermenting in one bacteria. Okay. Without going into detail, we took the gene from Zymomonas, alcohol dehydrogenase pyruvate decarboxylase enzyme, put it in E. coli, and we used mixed acid fermentation to produce ethanol. We produce 40 to 60 grams per liter of ethanol, which is 95% product yield, theoretical yield. In the lab we made. Okay, and then we did some couple of more gene knockout experiments. So when you go through fermentation, the organism not only make ethanol, it also make fatty acid, short chain fatty acid, long chain fatty acid, acetic acid, butyric acid, propionic acid. So you are not shunting all the carbon to ethanol, some byproducts are there, right? So we knocked out the genes that make lactate, the genes that make formate, we kind of knocked it out, took the gene out of the bacteria. So the only product the bacteria can make is ethanol. All right. So we improved the efficiency of ethanol production by tinkering with the DNA using recombinant DNA technology, putting genes from different organisms in one organism. And that's what we did. We improved the yield. This is what we call the processing cost. Remember, I put a bar graph. You can increase the efficiency. That's what exactly we are doing here. And then we did the pilot plant, and in a 25-liter bioreactor, and we tested that with improved E. coli. We only shunted to make ethanol. You can see the xylosic sugar going down. Bacterial yield is improved. When there is no knockout, you produce organic acid. When you knock out this gene, you make xylose come down completely. You make everything into ethanol. Your ethanol yield improved. All right, as your biomass yield. Okay, so these acids are not produced here because we removed the genes out of the bacteria. We improved the efficiency of one product that you wanted to make. Okay, yeah. Yeah. Oh yeah. If you want organic acid, you can make organic acid. Organic acid can be made into a value-added product. But our goal is to make ethanol. But you're right. There are companies that make organic acid. Okay, for like anaerobic digestion, when you make methane, the first step is hydrolysis step. You make a lot of organic acid. Organic acid is a value-added product, but our goal for funding agency to improve ethanol. Okay, so then we went to the sugarcane mill and got this bagasse. This is the bagasse, which is the waste in the sugarcane mill, and that's a composition of bagasse. And the total sugar available from the bagasse is from this much. And we used the bagasse and used our enzyme pretreatment with the fungus, and then we used our recombinant organisms. Okay, these are the enzyme come out of that, and then we used the fermentation technique, and you can see the yield goes up. And you can see the total sugar, that's the total sugar, and the glucose, the xylose sugar went down, the bacteria multiplied, ethanol went up. Okay. So we did in a small bottle to prove the concept, and then we went into the pilot plant and we said, yes, DNA technology works, we can make 95% ethanol yield, the process is efficient, but again, we need to put the economics into perspective. It's still expensive because this technology of tinkering with DNA is not cheap. Okay, so we are still working on that project. So that's one of the research project I have that I want to share with you. Okay, I think that's my last slide today, and tomorrow we'll talk about microbial lipids. Okay, all right. So I'll stop here. Is that good? Timing wise? Okay. All right. If you want any questions or discussion, if you want to have it tomorrow, if you're too tired, either way, I've occupied a lot of time. Yeah.
So how long the pretreatment should be in order
Check.
allow you for the
How long the pretreatment should be?
how long the pretreatment should be to allow for the ethanol production or any other energy production?
For the fungal one or the acid alkali pretreatment?
For fungal, I'm asking.
That we are still tinkering with it. The fungal enzyme, we are not using enzyme, we are using whole fungus. Okay, we use 2 weeks. If you look at the picture, I want to show the picture. So can you go back to that slide? Roll it to the last slide in that one. All the way down, the microbial lipids. Go to the last slide. Go through the last slide. Yeah. So if you look at this slide, just to show you 2 weeks, make it bigger. So look at this fungus. In a bag, we spray this fungus. Look at that. In 2 weeks, the fungus is chopping up lignin and softening the lignin, releasing the cellulose and hemicellulose. So our experiment is 2 weeks. Okay. If you're going to store your raw material for months, you got to have a critical point at which you need to stop. Otherwise, fungus will eat your glucose. You don't want that because you
How to calculate that critical point?
That's why you need more research. That's why your efficiency comes in. That's why we're talking about processing, right? So in our case, 2 weeks. For other crops, you got to do research. It depends on the feedstock, and in this case it's 2 weeks. You can see that fungus growing in there. Okay.
Thank you.
Any other question on the chat from there? Yeah.
Sir, during fungal pre-treatment, the lignin will be degraded, no sir?
Yeah.
Then after that, we will be treating it with mild acids. So during the mild acid treatment, won't the other compounds will be degraded?
Like cellulose, hemicellulose?
Yes, sir.
Yeah, we are using 24-hour time period. Our sugar, that's why I gave you sugar yield. I showed you sugar. So our sugar is okay. Sugar doesn't go down. But if you treat long hours of high acid, the sugar will break it down. But the fungus also will eat your sugar. So there is a critical point where you need to stop, you need to take out and process your biomass. Otherwise, the purpose of fungus growing on biomass is to break the lignin, convert the cellulose to glucose and grow on it. So we need to stop. We need to use the fungus to get the lignin out and then get your cellulose, hemicellulose. Yeah, that's the critical point. You need to do research and find when to stop it. Okay. So our idea is when you're going to store your material, when you're doing this in a bigger factory, during storage time, just spray the fungus, and then you do your R&D to how long you need to keep that fungus in the biomass. Okay.
Won't that affect that fungal action, sir? After, if you are storing it for 2 weeks or something,
Yeah.
after the fungal treatment, when you'll be using the acid pre-treatment, no, sir?
Yeah.
So won't that affect the fungal activities also?
We don't need fungal anymore. The fungus is to get the lignin out. We don't need the fungus. We get the acid treatment to get your cellulose, hemicellulose come out, and then you get enzyme process to go through fermentation stuff. So we are just loosening up the lignin using fungus. Okay? Yeah. Any other questions? Okay. All right. Thank you very much, and we'll see you guys tomorrow, I guess. Yeah.
You are getting the agricultural residues large quantities.
Oh yeah. We can produce things. We have a lot of things. We are not putting in the crop. They're going like here. They're going